So we looked at the base 10 system, and when I wrote it, I said the base 10 system has numbers from 0 all the way up to 9. So if we have base 10, the corresponding numbers that belong to that base are 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. I'm going to skip 9 and write 8. 8 must go 0, 1, 2, 3, 4, 5, 6, 7. 4, 0, 1, 2, 3. 2, 0, and 1. 2 is the binary system, and 8 is the octal system. 10, of course, is the decimal system. And comes an important base 16. Base 16 is used in computers, and so is base 8. Base 16 is what we call a hex system or a hexadecimal system. So zero, 1, 2, 3, 4, 5, 6, 7, 8, 9. And this is where things get tricky. We'll have A, B, C, D, E, F. So A would mean 10. B, 11, 12, 13, 14, and 15. Now you may say, well, why do we have to use A, B, C, D, E, F? Well, the problem here is the moment you go past 9, you end up getting 2 digits. And when we write it out, we cannot uniquely define as to what the numbers are because we don't know which digit belongs to which. So 16, base 16 is what we call hexadecimal. And hexadecimal would have those letters A, B, C, D, E, F, so that we can represent the 2-digit values, because any base must have numbers starting at 0 all the way up to 1 less than the base that we are speaking of. Now, key things to note. One zero one zero 1, 0. It's a proper base 2 number. Because it has 0 and 1. But 101331 is not a base 2 number. Because a base 2 number cannot be or cannot have the number 3. So at best, if I have to guess, I could say this is a base 4, 5, or 6. I don't know. So we have to specify as to which base we are talking about. All I can say about the second number is that it doesn't belong to base 2. But we don't know which base it would belong to because base 4 has the number 0, 1, 2, 3. So does base 5, so does base 6. So to distinguish the bases, we simply write it that we're talking about base 5 or we can say we are talking about base 6 and so forth. Unless we specify, we will not know as to what base we are talking about. The only base that is easier to recognize, or the two bases that are easier to recognize, are base 2 and a hexadecimal base. Because you see a bunch of letters in the representation, then it's probably going to be hexadecimal. It's easier to recognize, but of course it could be base 12 or base 13 and so on. Do we understand this process of recognizing as to whether something is a base 2 or not? We always base it on looking at the numbers that belong to a specific base. So a base 4 number cannot have digits bigger than 3. A base 5 number cannot have digits bigger than 5. Excuse me, 4. A base 7 number cannot have digits bigger than 6, and so forth. Here, we have to convert 43, which is in the base 5 system, to a base 10 system, or regular decimal base. How do we do that? Going to write the 2 digits. First off, even before we start, could this be a base 5 number? 43 is base 5 because both digits are less than or equal to 4. A base 5 number cannot exceed 4. So how do we convert it to decimal? Take the first digit, multiply by 5, since it is base 5, raise 0. Second digit, multiplied by base 5, so 5, raise 1. So 3 times 1, 4 times 5. So 3 equal and 20. When we add, we get 23. So the number 43 in base 5 is actually the number 23 in base 10. So what we have here is a valid base 2 number, and we want to convert it to base 10. So 10110 So 0 base 2, so 2 raise 0, 1 times 2 raise 1, 1 times 2 raise 2, 0 times 2 raise 3, 1 times, 0, 1, 2, 3, and 4. Okay, good. So 0, 2, 4, 0, 16. 0 times 1 is 0, but add them all together, I get the number 22. So 10110 in base 2 is the number 22 in base 10. So think about it this way. When you type the number 22 in your calculator or your computer is recognizing that 22 as 10110. And you may say, well, why ones and zeros? Because 1 means turning a switch on, 0 means turning a switch off. And that's just how all of electronics work, turning a switch on, off. So hence ones and zeros. Now what we have here is a valid base 9 number because every digit is less than 9. As I mentioned, this could be a base 8 if that 9 is not specified, but it cannot be a base 7 if that 9 is not specified. So we have 2, 0, 7, 3. You don't have to draw these arrows. Let me show you in a different way. Just like we expanded the base 10 system, we're just going to write it as 9 raised 0, 9 raised 1, 9 raised 2, 9 raised 3. And we are going to enter the values 2, 0, 7, 3. Let's see, 81 times 9, 729, 1458. 63 plus 3. We add them all together, it'll come to 1524. So the number A's in base 16 can be written in base 10. Since it's base 16, I'm going to write 16 raised 1, 16 raised 0, 16 raised 1, 16 raised 2. The value of A is 10. The value of C is 12. The value of E is 14. So 2,560 plus 192 plus 14. Add them all together, 2766. So A's in base 16 is simply the number 2,766 in base 10. So if you want to communicate the number 2,766 to a computer, the computer is going to translate it as ACE, as Ace. I have 1010E. Could the number above be base 2? Absolutely not. Reason being, 1, base 2 can only have 2 digits, 0 and 1. We've got that E. So it's more like it is going to be hexadecimal number. So I should probably specify it as 16, and we want to convert it to base 10. So 5 digits. Converting to base 10 from base 16. So 16 raised 0, 16 raised 1, 16 raised 2, 16 raised 3, 16 raised 4. Plug in the digits 1, 0, 1, 0, E. E is simply 14. 16 raised 4 is 65,536. 0, 16 squared is 256. Plus 0, plus 14. The answer is 65,806. So the number 1010E in base 16 is 65,806 in base 10.